Doesn't it feel like it's supposed to be time for spring break or something? So weird because we took the spring break so early, right? Yeah, I'm aware that this semester is a bit hard or feels a bit different than other semesters. And I see a lot of people are taking advantage of the fact that I have the Zoom open and that the Zoom room open and that I record my lectures. I mean, I feel like you get the most out of it if you're here in person. But I understand if like you're not feeling well or want to avoid sick people, or you just can't even on a day, right? I get that. But please know that if I see you here, I'm appreciating the fact that you're here. Okay. So we're going to do a couple of different things today. The first thing I want to try to do is work some more on the what I would like to do is work some more on some Monte Carlo, the problems I gave you at the end of last class, right? The scam games. Once we cover those, I think then what we will do is I'll go over the basics of GitHub and how to use Git in preparation for the start of our final projects. Because, and I don't mean this in a threatening way, I mean this in this is literally what I say. Today is the day to begin thinking about that, to begin thinking. Not to have an idea necessarily, but to think, okay, I need to come up with an idea. Make sense? So, and again, the first two parts of the final project are, which will be coming up pretty quickly, are brainstorming. That's the first thing we turn in, a brainstorming. And we turn in our brainstorming on GitHub. And then having an actual proposal about what you're going to do for the rest of the semester. Okay. So what we're going to do here, documents, we are going to GitHub. Teaching, no, classroom, ITP. Okay, so we're going to do scamgames.py. All right, so I've created an empty Python file. I'm going to be using VS Code today because that's what I feel like using. Okay, so now to review what our games were, let's take a look at our first game, which is we're going to show it a couple different ways. The first game, right? The idea is that I take from a standard deck of cards. Okay, from a standard deck of cards, I'm going to take out, I think it was 2 red cards and 5 black cards, right? 5 of the suit of clubs and spades, doesn't matter which, and 2 of the hearts and diamonds, right? Gonna flip them over so we can't tell what color they are. Gonna flip them over so we can't tell what color they are, and then we are going to proceed to we're going to proceed to to flip over cards. So, right, basically what we do is that we turn them all over so we can't tell which of these 2 are red, and we flip over 3 of them. And if we flip over only black cards, we get $1. But if we flip over, but if one of the 2 cards we flip over, but if one of the 3 cards we flip over is red, we lose $1. Make sense? And the person proposing this game is a jerk. So they say, hey, your chances of winning, I mean, that's like, I mean, the first card, you've got a 5 out of 7 chance, right? And then so as you get that right, your second card is a 4 out of 6 chance. And then when you flip over your third card, that's a 3 out of 5. Now, all of these are chances that are significantly higher than 50%. So I feel like treating this as though you're going to win half the time is completely fair, is what they say. But what these are is that these are, if we know statistics, and we know that these are not independent events, these are dependent on each other, which means that the appropriate association is not to treat them independently, but to multiply them together. We will learn that in statistics. But I'm just going to give you what the statistics answer is so we can check that when we do the Monte Carlo. Right, so I've taken a statistics class, and that means I know that what I should do is that I should multiply 5 times, I'm going to go ahead and multiply the tops first, 5 times 4 times 3. So that's 60. 7 times 6 times 5. So that means that the true odds were 60 out of 210, which means that our actual odds of winning the game are around 28%. Doesn't seem like it, right? Seems like you should have a better chance, but you don't. But this is just my math. And I mean, like, okay, I said I took a statistics course, but I was an undergrad at the time. So, it's been a while. And besides, I mean, like, that's math. What if you don't know or don't feel comfortable doing this kind of statistical analysis? What if you haven't taken a statistics class? That's where Monte Carlo comes in. Monte Carlo says statistics, hard, counting, easy. So let's go ahead and try this. So what we're going to do is that we almost always will be using, when we do Monte Carlo approximations, we'll be using the random module to do something at random. Now, random has like an amazing number of, we've got the source code here. Random has an amazing number of things we can do with it. We can, let's see. So like choice is one of my favorites. Shuffle is another one that's very useful. Shuffle just simply says give it in place. Also a big fan of sample, which returns a new list containing elements from the population while we're leaving the original population unchanged. So basically what this does is that it allows you to basically say, hey, we can draw a certain number of things. Sample though is not can be drawn, and it could be the same thing firing twice. We don't want to select that. This one, let's see, sample without sampling without replacement. So we can do that without replacement. Awesome. I'll check the actual docs. So there's things we can do to get around this. Will the final exam be on paper or on the computer? It will be on the computer, ideally. If you cannot bring a computer to the final exam, a paper copy of the exam will be provided for you. And I wouldn't necessarily worry. I will discuss the final in more detail as we get closer to it. You will know, broadly speaking, what the 3 questions are going to be, because I ask 3 large questions. In fact, I can tell you 2 of them right now. The first question is going to be given something, is going to be of this vein, not this exact question, but some variation of it. Given a file with a bunch of social security numbers, please create a new file that is the same file, but with all the social security numbers removed or censored or something. We'll learn either next week or the week, I think we'll learn next week how to do that specific thing. okay, using regular expressions. Regular expressions will make the job easier, but you can do it without regular expressions, okay? The third question will be, given a game, please do a Monte Carlo approximation and tell me, like, how often do the players win this game? Or how long does this game go on for? Or how often does this event occur in the game? Okay, those are two of the three questions. The other question will most likely be, given this code, please explain what in the world this code does. Please explain this. Okay. So it's either going to be that, or given this thing you haven't seen before, here's how to use it. And now use it to solve a problem. One of those two things. But I've come to like the, hey, this is code. Please tell me you can read code and tell me what it does. Which helps if you can run it. And again, on paper, if for some reason you can't bring a laptop or something to the exam, I will provide paper. And in that case, I will provide the output of the code. Although, again, that would be, if you can't do it on the exam on paper, I will make sure that it's fair. Okay. So if you can't do it on, if you have to end up doing it in person. All right, so let's go back to this, right? So so let's go ahead and create a function to simulate game one. This game that we're currently talking about. And in game one, right, that is, we have 7 cards, 2 red, 5 black, draw 3 of them. Okay, those 3 cannot be, and none of the 3 must be red. If you win, you win if none of the 3 are red. So let's go ahead and try this. So let's go ahead and call our deck of cards. And we'll, we'll call the, we'll put these into a list of cards and call them a deck. And we will have, I'll just manually code this in, right? 5 Bs to represent the black cards, 2 Rs to represent the red cards. Okay, now how do I ensure that this is actually, now what I'm going to do to ensure the whole flipping it over process so that we don't know where they are, what I'm going to do is I'm going to do random dot shuffle. And if you're dealing with a deck of cards, this is really what you want to do. And this will shuffle it in place. So what I'll do is I'll test it to make sure it's working. And I'll call game 1 down here and run it. And we see that we've got in 5 blacks and 2 reds. Got red, black, 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 black. Right? So it's coming up with a different configuration each time. Right? And R and B, they look like it looks like that, basically, that, we've got this. And so we've got ourselves no, and we don't, basically we end with the shuffle doesn't seem to be replacing anything, right? We end up with 2, we start with 2 red and 5 black, and we end with 2 red and 5 black. They're just in different positions now. Excellent. So now, once we've shuffled it, we have to do the whole process of flipping 3 over. Okay. So the first way to do that is to kind of approach it like the Monte Carlo method. Statistically speaking, if I'm playing this a bunch of times, there's no statistical difference between me drawing 3 cards at random positions, right? And me drawing the first 3. So we're going to see how to select 3 cards, these cards 3 different ways, okay? So the first way is I'm just going to use that, it's all statistically the same, which may not be an insight that you have. That's okay, but I want to show it to you. So what I'll do is I'll just simply say, hey, my draws or my flips or whatever, I'll call them my draws, are equal to deck from 0 to 3. So 0 up to, but not including 3, that is 3 minus 0. So that's 3 cards total, 0, 1, 2. Makes sense? And now what I'll ask is if R in draws, then I will return false because I lost. Else, I'll return true because I drew 3 black cards. So, and in either case, I will print, in any case, I will print out my draws. Let's see. Print out something, draws, and deck. And then we're just going to copy this into here. 1, 2, okay, and now I'll remove this because, and I'm going to say lose and win, right? We need to show that we're losing and winning, and I'm printing it out and returning because the printing will go away after I run it 10,000 times. We'll need to go away after I run it about 10,000 times. So here I lose because I drew a red card. I lose because I drew a red card. I won because I didn't draw a red card. And as you can see, the first 3 cards were black, 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 red, red, black, right? And if I run this again, win because I've got the same configuration. Black, 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 red, black, red, black. Okay, cool. So I see that I'm playing this game, right? And that does it. But this statement over here, that's subtle, right? That's subtle. Identifying, hey, the first, just, you know, grabbing the first 3 cards all the time. That's the same as doing it as doing any, that's the same, right? As you like, that's the same statistically as any other selection. But what if you actually want to, you know, simulate somebody actually drawing stuff at random from this deck, right? Because I'd also like to see, hey, is that statistically the same? So, sorry, I put that in the wrong place, method 1 or technique 1, whatever. So method 2 is I need to draw 3 cards, which means I need to draw 3 that means I need to select 3 of these cards, and those are going to be my cards. Now, the indexes of the cards aren't different, but the indexes are, right? Their indexes 0, 1, 2, 3, 4, 5, 6. So what I need to do is I need to select a number from 0 to 6 up to and including 6 at random 3 times and make sure I don't pick the same card twice, right? So what I'll do is I'll say, okay, indexes are the indexes I want to choose are going to be equal to a list. And what I'll do is I'll choose a card by doing, and so what I'll do is I'll create a while loop. While the length of indexes is less than 3. So while there's less than 3 things in indexes, this is what I'm going to do. I'm going to go ahead and I will what I will do is I will first, I have to generate a random index. So random.randint 0 to 6. Here it's inclusive. Random's the only place where it's inclusive. Okay. Choice is equal to random.randindex. Okay. So now I've just got to, and basically what I need to do is say, basically what I have to ask myself is, while choice, actually, if choice not in indexes dot append choice choice. So what in the world is going on here? So I'm saying, while we haven't selected three things, three of these indexes, right? We have 0 through 6. Those are the locations of the card. I'm going to randomly generate one. If it's not one I've seen yet, I'm going to add it into the indexes I've seen. But if it is one I've seen, then this if statement's gonna not fire. And so we continue on with the while loop and we generate another random number. Because, right, if we're selecting stuff at random, we don't want to have the same index. If we didn't have this if statement and just went directly to line 12, we could end up in a huge issue because we could be trying to select the same card more than once. We're trying to flip over 3 different cards, right? So what I'm going to do, so what I'll do here is, now that I have these indexes, I can say for I in indexes for each of these, I'll say, I'll put a draws over here. I'll make my draws over here. Draws is equal to, equal to an empty list, and I'll say draws dot append dec I. And what we'll see here is if I run this, I got to win because I selected 3 black cards. I got to lose because I selected black, red, black. And notice it's not giving me the first 3 anymore. Specifically, let's go ahead and see what our choices are. I will go ahead and print indexes. Okay. So here I went with cards 1, 6, and 0. So index 1, index 6, index 0, which gave me black, black, and black. So that was a win. 0, 4, and 2 is a lose. 2, 1, and 5. And yes, technically I could stop the game as soon as I drew the first wrong card, but I might as well go ahead and draw all of them. Okay. So that's strategy number 2. Okay. And we'll go ahead and put this over here, and I will comment out strategy 2. Or so method 2. Okay. I see pop up in chat. Why is the while loop less than 3? Because we need to make sure we have 3 cards in it. While length of index is less than 3, while there's been less than 3 indexes selected. Okay. Method 4 is to use the documentation. So random module Python. And we're going to use sample. Return a length of k length unique elements chosen at a population sequence sense. Used for random sampling without replacement. So in other words, we can, so let's go ahead and see how that works in idle just for a second. Right? If I've got, let's say a list here, L is equal to 1, 5, 6, 10, 11, 2, 3. Import random dot sample. I want to select from L 2 things. Oops. I want to select 2 things from L. Gives me 1 and 10. 6 and 11 this time. 10, 11, 10, 11, 2, 5, 2, 5, 10. It's random each time. right? And I'm just simply drawing out what I'm getting from these items. I'm just selecting 2 of them at random from here. Now here's the question. L is equal to 1, 1, 1, 2. Random.sample 2 things from here. So yes, it will draw, but it's not going to draw the same item twice. And essentially, this is in one line, the loop we just did. But you have to read through the documentation and test it to make sure. So method 3, use random. Dot sample. Draws is equal to random dot sample. So from our deck, we want 3 items. And then we run this a few times. Okay, so it seems to be working. We're drawing a random sample from there. Okay, so now what we want to see is basically what are the true odds, and do each of the 3 ways of drawing cards that we came up with, are they really the same? Trials. Does it really matter if I draw 3 cards at random versus drawing the first 3 cards all the time? So I'm going to do 10,000 of these games, and because if as a result, I'm going to comment out these lines, because otherwise I'm going to comment out everything that's a print, because otherwise we'll be here forever. So trials, for in trials. So we're going to do this for range trials. So we're going to do this loop 10,000 times. And what I'm going to do is I'm going to count up the number of times we win. We don't really need to count up the times we lose, because we can get that using math by subtracting the number of times the wins from the trials. So for blank in range trials, what are we going to do? We are going to simulate the game. The result is equal to game 1. So we get a result, which is either true or false. If result equals true, and I'm being verbose here, I'll show you that I can shorten this, then wins plus equals 1. Right? Because we get the result from the game. A true means we won the game. A false means we lost the game, right? Now we can just simply simplify this to, okay, if we're storing this result, we could just put that method call right in here. And because this is returning true or false directly, I could just simply do that. But that looks weird to some people and hard to read. So it's okay to break up your lines like this. So what we're going to do now that we've simulated 10,000 games is that we are going to print our wins and then our wins divided by our trials. So let's go ahead and run this. And let's go ahead and do technique number 1, which is taking a slice. Just doing a slice, like pizza. Everybody loves pizza. And we see that we won 28,000 times out of 100,000 about. So our result over here, 28, which is 28.397% of the time. Let's go back to our calculator. 60 divided by 210, 28.57. So that's pretty close, right? My Monte Carlo approximation is pretty close. So 28% of the time, right? We're only winning 28% of the time. So unfair game. Well, is it the same if we do this method? So let's go ahead and run it. And again, 28% of the time. It's never going to be exact because we're dealing with randomness, but approximately 28% of the time. This is close, right? And the more trials we do, the more accurate it's going to be. Right? And now this will take 10 times longer because I'm doing 1,000,000. Yeah, but definitely 28.5 now, and that matches up. So now let's do our final technique, which was sample. So in other words, I'm trying to say there's multiple ways to do this depending on the way your brain decides to tackle the problem. So random not sample from this, and we see that we get 28.6%. Yes. You want to comment out these things? Yep. Comment it out, because otherwise that's what you're going to get. So when you're doing your Monte Carlo approximations in the pig homework, remember to comment out your print statements for those for when you're simulating like a lot of games, because otherwise you'll be sitting there for a while. Okay. So this is an unfair game. It didn't really like, okay, when I told you it was scam, you were thinking, okay, maybe my chances of winning are around 40%, right? As opposed to 50. But this was 60. This was essentially a 30% chance of winning, less than 30% chance of winning this game. This was a honker of a scam. Okay, it was or as a line from one of my favorite movies, Zootopia. It's called A Hustle, Sweetheart. Love that movie, Zootopia. So good. Kids buddy cop movie. What's not like to look at? Especially the sloth scene with the DMV. That was the best. All right, so now what we're going to do is that we are going to add we're going to add 2 more black cards into the mix this time around, okay? For game 2. Okay, and in this time, we are going to be making a grid. Here we have, and I will be I'll go ahead and just draw them in. Let's see, green. 1, 2, 3. Yes. 1, 2, 3, and lay them out in a 3x3 grid. Okay. Okay. So what we have to do in this one is that we've got 7 black cards and 2 red cards. Okay. And so what we're going to do here is ask our player, okay, well, this game this should be fair. 2 of these face down cards are red. Flip over 3 in a row. So not just any 3. Okay. Flip over 3 in a row, like this, or this, right? One of those ways. And you win. The same thing. If you get all black cards, you win. If you get a red card, you lose. Okay. Everybody get the premise? Okay. Now, so let's just go ahead and work through this logically, right? There was 1, 2, 3, 4, 5, 6. 6 ways, 3 columns, 3 rows, right? And 2 diagonals. That means there are a grand total of, I'll write this in crayon font. That means there's 8 ways to win. 8 ways to win. But now let's go ahead and position 2 red cards pretty much anywhere. I'll go ahead and put them like this. Now, how many ways are there to win? 1, 2, 3, 4. There are 4 ways to win in this one. So half the ways to win are blocked by those 2 cards. But what if I put the red over here now? 1, 2, 3 ways to win. That's it. So more than half are blocked. And if I decide to put it like over here and make it asymmetrical, 1 way to win, 2 ways to win, 3 ways to win. So I'm going to posit there you never have a better than 50% chance of winning this game. Never. And that just depends on, and your luck depends on where those red cards are. So as you can see, even like without like doing like real statistical analysis, just by like mentally just using some pencil and paper, we are able to figure out, aha, this is a bit of a scam. So this one's going to be a bit trickier because we're going to be dealing with a 2D grid, essentially. But it doesn't have to be, because we can also use the same trick of statistically just of saying, oh, statistically, it's the same as flipping over this vertical, you know, this row. Right. And as far, so what we'll, so let's go ahead and say def. So what we're going to need to do, so the hardest part is going to be setting it up. So def game 2, right? We need, let's see, we need our deck now, or we can call it our grid, is equal to, or sorry, let's call it our deck, and we'll make our grid from our deck rather than worrying about the 2x2 nature of it right now. Because right now, while we're trying to figure out the order of cards, it's better to just treat it as one big list. Right, so what we'll do is we'll grab this from like we did from earlier, and we'll do the same. We'll just add 2 black cards. Now there might be, now part of me is going like, wait. Did I really type out 2 ones? Did I remember? Did I do it right? How do I know if it's right? 1, 2, 1, 2, 3, 4, 5, 6, 7. Wait, did I count that one already? You know, human eyes suck, for want of a better term. They're terrible. So is there a more exact way to do this? And there is. We can just use replication. So what I could do is say, hey, give me 2 R's, right? This trick. Give me 2 R's and concatenate that with 7 blacks. Make sense? 2 red, 7 black. And now I can do print deck, and we can see print game 2. And what I'll do and invoke that, and I'll just go ahead and comment out this stuff that we've already done. Okay, so print game 2. And we can see that we get our, we don't need print game 2 because it's not returning anything. Here we go, boom, red, and 7 blacks. And now we can do the same thing over here where what we did to shuffle it, which is random dot shuffle. Okay, random dot shuffle. Now what I'm going to do is unnecessary, but I think it's useful for you to understand how a 2D grid works, right? So what we're going to do here is we've got the deck, shuffle the deck, print out the deck, and shuffle, and shuffle, and shuffle, and shuffle. So the question is, how often am I going to win this game? So now we got to lay out these cards in a grid. I mean, we don't have to. I could say, hey, I'm going to just choose the first 3 cards because, you know, I could just basically do the exact same thing I was doing earlier, saying, hey, give me the first 3 cards. So I guess my chances of winning would be higher, because those first 3 cards would be across the row. But honestly, that doesn't necessarily give us the true odds. Maybe we'll see. So let's figure out what that is first. So, right, we'll take method 1, and we'll just do this right now to kind of figure out what our chances of winning are. And see if my hypothesis is that just drawing the first 3 cards is identical to drawing the same thing over and over again, which is, and nothing, and no choice is better than any choice. So let's go ahead and just try that out. So game 1 versus game 2. And it's going to say, hey, you've got a 41% chance of winning, which makes sense. We've added 2 cards. So, but again, this isn't a grid. We haven't laid it out into a grid. So how do we know, as a matter of fact? Okay, which is a great point. So let's just keep that in there as our estimate, 41, right? So let's go ahead and put this into a grid. So how do we do that? Well, what we're going to need to do is we are going to split up this, basically this into 3 parts. This will be the first part, the second part, and the third part. So what I can do is I can do that with slicing. So grid is equal to, and what it's going to be is that we've got like 3 different rows, right? Let's go ahead and break that up into multiple lines. Row 0 is equal to the first 3 cards, right? So we could do that like this. We could do that with deck 0, 3, get the first 3 cards, right? And then row 1, and then row 2. Okay, that would be 3 to 6, and then 6 up to, but not including 9 because that index doesn't exist. Print the deck and print row 0, row 1, row 2. Oops, I scrolled up. Oh, and I'm doing it 10,000 times. My bad. So probably should stop that. There we go. So what we've done a bunch of times, run it, and we've got, and you can see we split it up into 3 rows. Now we could also like manually append, like do a range for I in range 0 to 6, row 0 dot append deck 0 deck I. We could do that, but you don't need to. But to make it a grid, we're going to put that in, we're going to put each of these rows into a list. Assuming I can type. Okay. And if we print out our grid, we're going to see that it's a list of lists. This is a 2D list, a 2-dimensional list. A better way to think about it is like a grid or a matrix. But what is index 1 in this grid? Or index 0? It is that it's the first list. It's this first thing over here. Index 1 is the second list. Index 2 is this third list. Make sense? Basically, because it's a list of lists, it gives you the entire thing. The entire list. Right. So one way to print it out a bit better would be for row in grid, print the row. Oops. And now what we're going to get is we get black, red, black, red, red, black, 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 black. So we get all those ways of winning. Okay. So Okay. Now we have a couple of different ways to do this. So again, I could just simply check what row 0 is and add that up. But I think it might be interesting if we simulated the whole, okay, select a way of winning, right? Select a way of winning, okay? And then we're going to figure, and then we're going to see if that matters, if randomly selecting the row that wins rather than just selecting the same one matters, because it might. It might. So there are 8 selections, right? 1 for each row, 1 for each column, and then 1 for the first diagonal and the second diagonal. Okay. So what I'm going to do is I'm going to do, let's see, I'm going to do, let's see, selection. I'm sorry. Let's see. If choice is equal to random dot brand int, and then there's 1 to 8. There's 8 different. Sorry, there's 0 to 7 because there's 8 different ways to do this. All right. So the first 3 ways are going to be fairly straightforward, which is if choice, and I'm going to be pedantic here just to kind of make sure you understand how 2D arrays kind of work. So choices 0, 1, and 2 will refer to get selecting row 1, row 0, row 1, row 2. Choices 4, 5, 6 will do column 1, column 2, and column 3. Sorry, column 0, column 1, column 2. And then 7 and 8 will be the diagonals. Okay. So it might be a bit repetitive, but if choice is equal to 1, if choice is equal to 0, then we're going to do row 0 first. So what are the things that are row 0? Our draw is equal to, let's go ahead and make our draws. What do we call it? It draws. And then we will just simply do the same thing we were doing over here. Because we're not just selecting 3 at random, we're selecting 3 at random in a specific way. Draws is equal to an empty string here, empty list. And what we'll do is say, we'll say draws equal to, and it's going to be a list of 3 items. We could just simply say it was equal to row 0, but let's select the items from grid directly. So this is row 0, row 1, row 2. And then these elements in them are in columns. So, and the way we do that here is just like with matrices. So grid 0, 0 for row 0, column 0. Grid 0, 1 for row 0, column 1. There should be, why is row 2 till 9? 7, index 6, index 7, index 8. These are, there's 9 items total. There's 9 items total in this one. Grid 0, 2. Right. So row 0, and then column 2, or the 0th list and index 2 inside of it. Now for this one, we can just do a bit of copy pasting, right? Because it's going to be the same for row 1, and row 2. So row 1, row 2, what we do here is do 1. You're going to replace that with 1, 1, and 1. Row 1, column 0, row 1, column 2, row 1, column 3. And then finally, row 2, column 0, row 2, column 1, row 2, column 2. Okay. I'll just say 3 over here. And then, yep. And then the outer brackets are just making sure that they get put into a list together. Yes.
So I just use the variable choice instead of using like 0, 1.
You could totally do that. We could totally do that. But once we get to choices 3, 4, and 5, it's going to make a bit less sense. Okay. Although there are ways to simplify it. We could certainly do. So his question was, why instead of doing 3 lines, why not do this one? And the answer is because some people may have just not had exposure to the 2D or 2D lists yet. So I figured I might as well be very deliberate about how I did that. But if choice is less than or equal to 3, right? Again, I'm being super deliberate about this. There are multiple ways to do this one. If choice is less than or equal to 3, instead of doing this, we could just do choice, but not, sorry, less than or equal to 2, right? We could do choice, and then choice, right? Where that number goes in there. But once you throw variables, when you're just starting out, it can be very scary looking. Now, what about 4, 5, and 6? Well, those are the columns. And what we do over there for choice is equal to 3. What changes now is the column. So now we're going to work with column 0. So row 1, column 0. So the column is going to stay the same while the row changes. So rows 0, column 0, row 1, column 0, row 2, column 0. Make sense? So, and again, and what changes over here? So here with these 3, the difference was what the row was. With this one, the difference is going to be what the column is. So the second number. So 4, 3, 4, and 5, grid the column. Column 2. Okay. And to answer you and to play off of what you were doing, which is clever, what we could do is now say, instead of this, so this is alternatively, if we wanted to do it like this, we could say if choice is 3 or 5, 3, 4, or 5, right? If the choice was 3, 4, or 5, then what can we do? We instead say 0, 1, 2, choice, choice, choice. So here, right, it's the choice that stays the same. It's the column that stays the same, right? Make sense? And now finally for the diagonals, which are 6 and 7. Okay, for 6 and 7, what we're going to do is we are going to say, so row 0, column 0, row 1, column 1, row 2, column 2. So here it's matching 0, 0, 1, 1, 2, 2. And then here we have row 2, column 0, row 2, column 0. Then row 1, column 1, and then row 0, column 2. There's just not a clever way to do that one. So these are, so now we've got our selection over here. And now what we can do is we can run it to make sure that we didn't have an error. Okay. And now let's go ahead and simulate game 2. And what we're going to be asking again is that if there's a red in there, we lose. And again, it's the same thing. This is statistically the same as choosing the first 3 cards, which was a 41% chance of winning. It was still a valuable exercise, though. So before we continue on with the, before class ends, we still have 25 minutes, and I do want to move on to something that's final project related. Yes? Oh, this does it for the rows and columns, which is a bit easier. That's equivalent to the first 6 ones we just did. But again, if I throw a variable in these things, and it's then that makes that really scary as opposed to just moderately scary. So now I will share this, and I'll be sure to share it on my GitHub. So what is GitHub? Anyway, so let's go ahead and go to GitHub. So one of the requirements for the final project is that it's going to be on GitHub. GitHub got bought out by Microsoft a number of years ago. GitHub was a reputable company before then, and it's still a reputable company. Now, GitHub is a source version control service. So first off, what is Git? GitHub is a place for storing source code using Git. What is Git? Well, it was invented by Linus Torvalds. Who is Linus Torvalds? Anyone? Really? No one? Yes, he is the maker of Linux. Linus Torvalds made Linux. And Richard Stallman would very much like me to point out that actually it's what is commonly referred to as Linux is actually GNU/Linux. But anyway, that's a whole can of worms there. But Linus Torvalds is a it's a Finnish American, and he created the Linux kernel and did stuff. So Linux was meant to be kind of a kernel for that kind of emulated the old Unix environment. Unix is the basis for a lot of computers, including those of you using Apple computers. That's running often off a version of Unix. So, but anyway, he named Linux after himself. And then also he created a distributed version control system, meaning a way to keep track of files, which is what we're going to look at. And he called that Git. And he also jokes that he named it after himself. And if you know, that's quite a bit of self-deprecating humor if you're familiar with British slang. So anyway, so Git can be easily installed by going to git.cm.com, and by itself, you could use it locally on your own computer. But the point of having it on GitHub is kind of the place to build a portfolio. I'll sign in on my account. I mean, it is how one of my friends got scouted by Google. So by having a GitHub repository that a recruiter found. So although he didn't get hired that time, he got hired much later, and then he quit, and then he got rehired. So anyway, hold on. Oh, right. So in my authenticator app, they aren't going to send me a text message. Yeah, two-factor authentication is good. You should use it. All right. So GitHub is basically a place to share and put basically projects. Projects are called repositories on GitHub. And for instance, over here, I have a classroom folder, and I have a bunch of folders for like my data structure stuff. So like the source code for all the data structures I write from scratch in my videos for that class. So here is Java. But the main thing about GitHub is that what makes version control valuable for large projects is this history over here. It doesn't just save it the latest version. It saves every version I've ever made of this, which is important because that enables, but not only that, because of the way that it's set up in a large programming environment, right? You could be working off a common base called the trunk of the code, right? And let's say you want to add a new independent feature. You can check out this branch and work on it. And then somebody else can independently, without conflicting with your stuff, check out a branch from the trunk and work on it. And they might decide that their thing is no good, or they might not. Doesn't matter. Doesn't affect the main branch. But when you fully test and add that feature you want, you can merge it back in to the trunk. I know that's kind of weird in terms of a tree, but I like to say that, you know, programmers don't necessarily get outside too often, so they sometimes forget what trees look like. I mean, otherwise, why would we make our trees upside down with the root at the top and the leaves at the bottom? Obviously, it's because mathematicians and computer scientists don't go outside and appreciate nature so much. So, but in practice, what this means for you is that you can make a repository and host your code on it. And it's there for anyone and you can make it either public or private. So what I've done over here is, after making this, so once I'm logged in, there's a couple things I can do. I can go over here to this add button, or I can click on new to create a new repository. This is generally the easiest way to start up a repository. Okay. Give it a name. If you don't have one, they'll suggest it for you. It just needs to be unique for your repository, right? For your account. So you can have the same project name as somebody else's stuff, but as long as it's yours. Okay, so let's go and call it Spring 2022 demo. Okay, it's public, meaning everybody can see it. And then we can initialize this with a README, and then you can do stuff over here. I'm going to just click the add README file, which gives me a README, and then clone and create repository. And so it creates this repository on there with a README file, which just simply has this. If we look at the source code, it looks like this for that file. This file is a special type of text file called .md, or Markdown for short. It's a Markdown MD file, which is short for Markdown, which is a type of markup language, but it's Markdown because it's short. And you can see that my first commit was so many seconds ago, and it keeps track. So now what I can do is, on my computer, I can use the hard way to do, the terminal way to do this is I could use the Git thing that I've got installed from that website, Git SCM, to do this. And I could say Git, and what we do is we clone this. I create a local copy on my computer. Okay. So Git clone, and then I get the URL. So here, if I want to clone it, I would just simply say, okay, there's the URL. And notice there's other options there. But anyway, this will clone it and connects to it, boom. And now, over here, on my computer, if I go to my over here, we'll see I have a spring 2021, spring 2022 demo over here with a hidden folder in it. You can see it's transparent. That's what transparent means, it's hidden, which these are just Git stuff for it. This is just all the like information on how Git is supposed to work. And yes, open it. And there's the same source code. I'm going to make a change to this file. This is a demo of Git for my class. Save. Okay. Save. Now I've saved it over here, but I should mention that that does not, of course, affect anything. That was on my computer. It does not, of course, affect anything online. And in fact, Git doesn't really even care that I saved it. In order to register a save, to like save a snapshot of what you're currently doing, we create what's called a commit. Git commit, and then we specify the file that's changed. Now, this is I'm showing you how to use it using the command line. You're probably not going to use the command line. There's an application which I'll show you in a bit. Git commit. And I think it's read. What is it? It's what is the file? Oh, it's readme.md. Readme.md. Oh, I'm not in there. I have to go into that repository. Git. So cd, so change directory into spring 20. No. Yes. It already exists, so I don't need to add it. So git commit -a, or sorry, readme, and now saying, hey, write a message, and it brought up Vim for me because it's being super helpful, and many of you probably won't find Vim that helpful, but I know how to use Vim, relatively speaking. Added line to readme, and this is basically saying what is the change I made. But there we go, and then so that created a snapshot. I did not make this on my desktop. Desktop is like the place you do not want to keep this because your desktop will get there. There are different, so let's keep going. This is another line. So I saved it. And also, give me a second, trust this window. So now that it's trusted, by the way, it's hard to see here, but also Visual Studio Code recognizes that I'm working in a folder that's attached to a Git folder. I will go over this again, and I have videos from the previous semester. And it tells me down here, hey, wait a second, you've got changes made that you haven't committed, and you've made changes that you haven't pushed to the internet yet. You haven't pushed it to the repository yet. So one of the things that's wonderful about code is that it integrates automatically with GitHub, but it's unneeded. So I've made another change, so I'm going to commit that. A second line, and this is just kind of to show you what happens. Now I'm going to put it back on the internet. Git push. If you haven't signed in before, it will probably ask you for your username and password. You need to give it, and then it will make those changes because they don't want random people writing stuff to your account. And now if I reload this page, 3 commits. This is another line. So if we take a look, initial commit, which was blank, added a line to readme, and as you can see, the changes that got made. And then a second line, right? So we can see how things have changed through this. And this is useful for saying, hey, I've worked on this, and I slowly worked on this, and I made changes. especially if you're working on a project that is based off of somebody else's project and you want to fork it. Forking, meaning making your own branch with your own changes. It's a very beautiful system, but at the end of the day, a lot of times it does come down to this. This is Git. It tracks collaborative work on projects through a beautiful distributed graph theory tree model. Cool, how do we use it? No idea, just memorize these shell commands and type them to sync up. If you get errors, save your work elsewhere, delete the project, and download a fresh copy. That is painfully true. Most of the time though, when I'm working with Git, a lot of the times, I use their desktop application, okay? Here, this is identifying, hey, the file in your classroom, you just have, there's a new file in the scam of the scam games we worked on because I saved it in my classroom folder, which is a Git, which is something I manage with Git. So now what I'll do is I say, okay, added, yeah, this is tiny, added new file, commit, and push, and it handles it for me. But suppose though that and for me to get something from this, I just simply change my repository, add clone repository, filtering my repositories. Let's see, is there a way to options to make this appearance now advanced? No, okay. So options. So I'll just simply do Spring. So add clone repository, and it will, and this is just simply saying, hey, you're in GitHub, so we can look. And says, oh, Spring 2022 demo. And it's cloned it in Documents, GitHub, and it'll automatically choose where to clone it for me, which is different where I've already put it, by the way. That's deliberate. It's kind of going to simulate me working on two computers, okay? So now let's go ahead and I've got this cloned to my computer. And I can now go ahead and open this in Visual Studio Code just with a click of the button, or I can open it in my Explorer. Right, and there's the README file again. Let's create a new file. A Python file, hello world. So create a text document. We're going to call it hello.py. Okay. And if we go over here, it's detected, hey, you've got a new file that's empty. I can commit that and I can push it. And now on the internet, on GitHub, we'll see that a second file's appeared here, an empty file, which is useful because now I can go to any computer and download it, which is nice. It's good for syncing your work between two computers like that. Or, so here I'm going to go print hello, save. And again, another change has been made. Commit it, push it over here. Okay. So now let's pretend I'm over here in the terminal, and the person and me working on the terminal is me on a different computer. It's on a different location in my computer anyway. It's in a different spot. So now, or I'm on a different computer and I did some work. I need to get what I did. The way we do that is by polling, right? We push to get stuff, put stuff on, to put stuff on the repository. I pull to get stuff off. Git pull. And it made the updates that were needed. Now here's the interesting bit. I'm over here on this one. I'm going to say print It's a nice day in this file over here. But in this repository, right, it's a different copy of the file. Suppose I'm another person working on the project, okay? I'll make a change, print. Today is rainy. Okay. So I'm going to go with the automated system first. Okay. You're going to so the automated system is going to commit. They're going to push it, or I'm going to use this one. Okay. And now let's go over here to the terminal because the errors look scarier there. Git commit, and I'm going to change to load up pi. Added a line about rain. Okay, and now I'll git push, right? So suppose somebody else was working on it and I was working on it. We both made changes and I'll push. So it says, hey, you can't push because you're behind. You don't have the latest version. That's solved by polling. Now, in the vast majority of cases, if you're working on one file, somebody else is working on another file, it handles this automatically. In worst case scenario, though, you get something like this, what's called a merge conflict, where basically it doesn't know what to do. And it will show you something like this, where it says, hey, we have this file that has print hello. You want to put in today is rainy, but this is what we pulled down from the internet. It's a nice day. We don't know how to change how to rectify these changes. Okay. So I can either, and what I do is I just have to manually delete what I don't want in this file. So I'll say it's rainy. Today is rainy. That version's going to win. And now I will go ahead and push it. Now this, or sorry, git commit -a means all the files, and then this says, hey, it's automatically it's a merge. So git push, and now all is right with the world. And now but that's generally how, if it's painful, and most of the time it's not painful to do that. Here I've said, oh, there's 2 commits that you missed. Okay, I'm going to pull this and update my code. Most of the time, it's not painful. Most of the time, it can figure it out. Print. So this is, sorry, print. This is line 2. Save. This is line, sorry. Print. This is line 4. Save. Okay. Hit commit -a. So this time I'm going to commit from the terminal. Yes.
After you're done with this, what's
The repository. The repository link. Okay. And now over here in the automated system, which again, I highly recommend you use, I'm going to commit this one. And I'm going to try to push it, but it says, hey, you've got newer commits. You have to get them. Okay, I'm going to pull it. And it says, and now it says, hey, we went ahead and created, and here we can see the entire history. And it may be hard to see here, but it went ahead and auto merged for me, because it was able to figure it out, because there's no conflict between the changes that were made on this computer and the changes that were made on the other. So online, we'll see if we check hello line 4, hello.py, did it. So before I let you go, this is what's going to be for the first step of the project, okay? So for the first step of the project, you're going to create a GitHub repository for your final project. And you're going to upload a file to it, which you can do. You can just upload a file to your GitHub, or you can just create it like I had been doing earlier. What you're going to get is so here's proposal and GitHub Lab. So you'll have this markdown file, right? Which is a text file. You'll want to download it and put it on your GitHub account and fill it up. Specifically, you're going to be filling out this. This is due April 1st, which is what ideas do you have for your final project? If you plan on collaborating with your with one or two classmates, who are you planning on collaborating with? And do you have any questions of your own? That's the first step of the project, okay? You upload that to GitHub, and then you just share the URL of that repository with me. In other words, where your file is. And your TA should hopefully be able to walk you through this. If not, I can go through this again on Tuesday in more depth. But it is not necessarily something to freak out about. I just did a lot in 20 minutes, so that's okay. I will be discussing the final project more in depth on Tuesday. Okay, as well as talking about some ideas, as well as ideas I have already provided for you. Okay, so I hope you have a great week, and I will see you again on Tuesday.